Hi, everyone. I'll be starting the lesson right now. Today, we're going to talk about atomic mass, specifically the isotopes and the periodic table. So we'll discuss in depth the periodic table today and some trends. So for the homework I assigned last week, the class average was a 4.67 out of 6, which is pretty good since my problems tend to be a little more on the challenging side of things. So you guys did well on the homework. For this week, there's going to be 5 questions in a Google Forms quiz under the Classroom tab in Google Classroom today. So around tomorrow, I'll post the homework for this week, and there's only going to be 5 questions. And if you have any questions or suggestions to improve this course, please email me at this email below. I would love to hear about feedback and how I could improve these lectures. So today we're going to talk about atomic mass and isotopes. I briefly covered this last week, but this week we're going to get more in depth. And then we're also going to get more in depth in the periodic table and some trends of the periodic table, like if an element is a metal, non-metal, or metalloid. And then we're going to talk about chemical formulas. This is going to help us get started into learning about reactions in the next lesson. So we're going to learn what the chemical formulas are and what they mean. And at the very end of the class today, we're going to tackle 2 US NCO problems. So these problems are challenging Olympiad problems. If you don't know what Olympiads are, they're exams basically for high schoolers that usually culminate in an international competition where you compete against other countries. And there's a chemistry exam, and it's quite competitive. If you like chemistry, I would suggest you, once you get to high school, to start looking into chemistry competitions or biology competitions or even math competitions. There's also physics as well, I believe. So we're going to get started with atomic mass and isotopes today. So isotopes are atoms with the same element that has a different number of neutrons, but same number of protons. So let's remember last time, an element is basically atoms that share the same number of protons. So if you have 1 proton, then it's automatically a hydrogen atom. But there's something called isotopes, which means that they have a different number of neutrons. So see, this one has 0 neutrons. This isotope of hydrogen has 1 neutron. And this isotope has 2 neutrons. So isotopes are atoms of the same element with different number of neutrons. And all of these have 1 proton. And we have a name for these. They're called protium, deuterium, and tritium. And just to recall, we learned about this nomenclature last time. The H is the atomic symbol, which is basically the 1 or 2 letter abbreviation for atom. In this case, H stands for hydrogen. The top number is the number of protons plus neutrons. So 0 plus 1 is 1, so the top number is 1. And the bottom number is the number of protons. So as you can see, in all 3 of these, the bottom number is always going to be 1 for any single one of hydrogen because it has 1 proton. That defines a hydrogen. But they have a different number of neutron, so these atoms have different masses. This has a mass of 1. This has a mass of 2 because 1 plus 1 is 2. And this has a mass of 3. So this isotope is 3 times as heavy as a protium. So that's what an isotope is. They basically have the same number of protons, but different numbers of electrons. So the chemists had a scale called the atomic mass scale. It's based on 1 atom called the carbon 12. So carbon is the most common element in a living organism. So we're made out of mostly carbon, animals are made out of carbon, and basically anything living. So carbon is living, the thing that makes up most living things. And if you study chemistry further, you'll study a branch of chemistry called organic chemistry, and it focuses on the carbon atom specifically. So scientists defined the atomic mass unit as 1/12 of a mass of a carbon-12 atom. So they arbitrarily defined an atomic mass unit, which is called an AMU. So the atomic mass that you see on a periodic table is the weighted average of all natural occurring atoms and isotopes. So in the previous slide, I was talking about isotopes having a different number of mass, different mass based on each isotope. And the atomic periodic table is the weighted average of all of them. And then I want to introduce one more definition. The fractional abundance is basically the proportion of an isotope that an atom has. So for example, carbon 12, it's 98.9%. 98.9% of all carbon atoms are carbon 12. Oh, this should be carbon, sorry, not neon. Carbon 12. So the fractional abundance is just 0.989. And then there's a carbon 13, which has a fractional abundance of 0.1011. So from the natural abundance, we can calculate the average atomic mass. Since this has a mass of 12 and this has a mass of 13, we can just multiply these two numbers together and sum them up, and that would give us the atomic mass, which is found on a periodic table. So if you do 12 times 0.989 plus 13 times 0.011, you can get the atomic mass to be around 12.01. So if you do the calculations in a calculator, you'll get 12.01 AMU. And that is basically what the periodic table says the average weight for a carbon atom is. So this is how they calculate the average weight on a periodic table. So we're going to do another example of this. So please type in the answer in the chat once you get it. Basically, I want to ask what's the atomic mass of chlorine given these isotopes and fractional abundances. You don't have to give me the complete answer. You can show me the multiplication and addition in the chat if you want to answer, but try out this problem to find the atomic mass. Remember, the fractional abundance is the proportion of all atoms that contain a certain isotope. Some people got the right answer. Someone asked to explain. Yeah, I'll explain it right now. Remember, the atomic mass is not the average of these numbers. You have to take account these proportions. Basically, we're trying to calculate a weighted average. So I'll give you a few more seconds before I give the solution. A lot of you got it correct, which is good. So basically, we just take a weighted average of the numbers. So the isotope of chlorine with the mass 35 has a fractional abundance of 0.76. So you do 35 times 0.76. And then you add the other isotope of chlorine 37, which has an average of 0.24. So you just take a weighted average. Oh, I had a question of isotope. An isotope, remember these atoms of chlorine have different number of neutrons. So some of them are heavier than others. So 76% of all chlorine atoms have a weight of 35, and 24% of all chlorine atoms have a weight of 24. So we want to find the atomic mass, which is the average mass of all chlorine atoms. So we basically just take a weighted average. So this is how we do the weighted average. And then when we actually calculate it out, you get 35.48, which a lot of you had. Or you can just give the first part, which is perfectly fine if you don't have a calculator. And we could look at a periodic table right here, and it has the weight right here, 35.45, which is really close to the weight we calculated. There's a little discrepancy, but that's because of the rounding errors in the fractional abundance. This isn't exact, this is just a rounded value, so we're gonna have some rounding errors in our calculation, but that's fine. Someone asked if they rounded this to 36. That's fine with sig figs, but we want to be as precise as possible. So for these calculations, I would generally go to 2 sig figs to be precise. This is different than the experimental errors and sig figs I talked about last time when we were measuring and things aren't precise. These values are actually precise. So we want to do regular mathematics with them, if that makes sense. And the isotopes have mass 35 and 37. Yes, that's correct. So chlorine has 2 isotopes. One of them's chlorine 35, and one of them's chlorine 37. And those are the 2 major isotopes. So we're gonna do another problem, which is the same thing, but a different element. This one has more. So what is the atomic mass of chromium given these isotopes and fractional abundances? One thing to watch out on this one is that the atomic mass is 50, 52, 53, and 54. It skips 51 because 51 is not a common isotope of chromium. So it sometimes does that, where 50 is pretty stable, but 51 is just not stable. And there's barely any of them. So please type in your answer in the chat when you get the atomic mass of chromium. So I had a question that asked, what do you mean by stable? So some isotopes are not stable due to properties we won't talk about now, but stable molecules are basically molecules that can exist on its own and not decay because it's unstable. If there's too many neutrons, or if there's an odd number of neutrons, usually those isotopes may not be stable and decay into other isotopes. I'm getting a lot of correct answers in the chat. Yeah, unstable isotopes would decay. The most common decaying isotope is uranium-235, and that's basically how they power atomic bombs. So unstable isotopes will decay. Okay, I'm gonna start solving this problem now. So basically we take the mass number and we times it by the fractional abundance to give a weighted average. So 50 times 0.04 And then the next number, 52 times 0.84. And then we're going to do 53 times 0.1. And then we're going to do the last one, which is 54 times 0.02. And then once you put that in a calculator, we'll get our answer. 52.06. The periodic table is 51.996, which is pretty close. We're slightly off due to rounding again. But that's basically how they calculate the atomic weight on the periodic table. They measure all of the natural occurring isotopes and they find how abundant it is and take a weighted average. So in your homework this week, there's going to be one problem on this, I believe. I had a question that asks, what does 3D54S1 mean? That's basically the electron configuration. It tells you the highest number of electrons in the atom. So there's a 4s electron, and then it has five 3D electrons. So it basically just tells you the outermost electrons. We'll probably cover this in a later lecture, electronic configuration, but basically by looking at the outside electrons, you can see the properties of this atom. That's a good question. Yes, there are different types of electrons. Well, electrons aren't different, but they each take a different orbital. And they react differently, kind of. So the next thing we're going to cover is the periodic table today. So in 1869, there was this Russian chemist called Dmitry Mendeleev. He had a dream. He was trying to figure out if there was a pattern between the elements that he discovered. Back then, they didn't discover all of the elements we have today, but they had like half of them. And he was trying to see if, because some elements react similarly, so he wanted to see if there's a way to organize the elements. And he had a dream that he organized them by atomic mass. And when he woke up, that's what he did. And he found that he could place them in a table called the periodic table, and each column would have similar properties. But today, we order the elements on the periodic table by atomic number, which is the number of protons instead of mass. But Dimitri's periodic table was pretty close to the one we have today. So this is the periodic table. It has 118 elements. So here's hydrogen right here. Here's hydrogen. Here's helium. I had a question that says that one of your science teachers says Dmitry Mendeleev had no social life. I don't know if that's true, but a lot of big name scientists usually aren't that social, so that's probably true. But we can arrange all of these elements in a table where each group, so like wait a second. So basically every one of these elements in this vertical group, they all share similar properties, which we'll talk about later. I had a question that asked, why are they in different colors? Do the colors represent something? And the colors do actually represent something. If you can see down below, the green are called the alkali metals, and these share similar properties, which is basically what I said. They all react similarly and they share similar properties, Like if you add them in water, they'll all burn up into flames. And then these red ones over here, they're called the noble gases. Basically, they're known for not being reactive at all. So they're very stable compounds, probably the most stable compounds on Earth. And they're all color-coded. So it basically talks about properties. So now I want to introduce a naming called period versus group. So a period consisted of elements in one row of the periodic table. So for example, period 1 consists of hydrogen and helium. In a period, they do not share similar properties at all, so they react completely different with each other. But the one thing they do is that they have similar sizes. So this hydrogen atom has 1 electron because it's neutral and it has atomic number of 1. So that basically means it has 1 proton and 1 electron. And helium has 2 electrons. So if they're in the same period, that means the electrons fill the same outer shell. So in a hydrogen atom, there's this 1 proton, which I'll color in red, and the electron, which I'll color in yellow. So this has 1 electron. In a helium atom, we'll have 2 protons, and we'll have 2 electrons. And they share the same ring, as to speak. So these 2 electrons share the same orbit. I had a question that asked, why is there a minus sign on the electron? There's a minus sign on the electron to show that electrons have negative charge. So that's the purpose of the E. I mean the E minus. The periodic table, I had another question that asked, how did the periodic shape form? The periodic shape formed because they wanted to align every element that has similar properties. So all of these elements have similar properties. And then they figured out helium had similar properties to these elements. So they put off helium here. And then they basically just aligned them with similar properties. Now, the only different part is these metals called the transition metals. They all share similar properties. So that's why they put in that kind of shape. But in these groups from 1 to 8, they all share similar properties. And that's why there's no group number for these transition metals. And then once you go to the 3rd atom here, you need another shell for the electrons. So you'll have 2 shells. So for lithium, you have 2 electrons in this shell and then another electron in a further shell. So that basically means lithium size is going to be much bigger than hydrogen atom size because the only 2 electrons can fit in this first shell. So another electron needs to go on the outer shell. But as you can see, as you go further away, you can probably fit more electrons in this shell. So general rule is that 2 electrons can fit in the first shell, which account for these 2 atoms. Then 8 electrons can fit in the second shell. And then the third shell, 18 electrons can fit. So as you go further away, you can fit more electrons in the shell. I had a question that says, so the elements that are in the same row are related and the elements in the same column are also related. The ones in the same column, which are called groups, which I'll talk about in the next slide, they share similar chemical properties because they have the same number of electrons in the outer shell. But in the periods, they don't share the same properties, but they share roughly the same size because the electrons fit in the same shell. I had another question that asked, why is the last group called group 0? Isn't it supposed to be called group 8? Yeah, I think it's a typo. It should be group 8. So basically a period basically has the same number of electrons in each shell, but it has they share no chemical properties to each other. So now I'll talk about groups. which is groups consist of elements in one column, and they do share similar properties. In the next slide, I'll talk about this group in red called the alkali metals, from lithium, sodium, potassium, rubidium, cesium, and francium. So in this picture, as you can see, this is lithium. I had a question. It says, are the elements at the bottom the same group as the element above it? I'll go back. So yeah, a group is basically a vertical, vertical column. So like lithium, sodium, potassium, so that's a group. A period is a row on the periodic table. And that's why they're color coded here. Oh, the island one. Oh, these are not a group. As I was saying earlier, these metals called the transition metals, they behave in strange ways. They're all pretty similar to each other, but actually this is actually a row. This actually belongs, it says 57, so it belongs right here. So no, even though they're colored the same, they have slightly different properties, but all of these transition metals usually have similar properties to an extent. That's a good question. As I was saying, in a group, this is the first group called the alkali metals. As you can see, when you put them in water, they all cause a fire, sort of. And the first one, lithium, it's not that much. But as you can go down the periodic table, sodium, potassium, they get more and more reactive with water. So it shows you that they have the similar reactivity with water. So that's the properties of a group. And I would like to go back for 1 second. And like group 18, they're all gases and they're all inert. So they usually don't react. So they also share a similar chemical property. So let's recap. So elements in the same period don't share similar properties, but they share a somewhat similar size because they have the same number of electrons in the outer shell. Electrons in the same group share similar properties. So group is up and down, like the color-coded ones here, because they have the same number of valence. They have the same outer electrons, so they bond similarly. And I wanted to go back and do one thing. So here is one atom called phosphorus. So it has similar properties to arsenic and this element down here, which is antimony, SB for antimony. It's kind of blurry, I'm sorry. But it does not have any similar properties like aluminum or silicon. I had a question that asked, is the periodic table completed? So these last elements down here, we couldn't find any of them in nature, so chemists tried to synthesize them. They last for a few, they don't last forever. We can probably try to find another element, but it's usually human-made and not found in nature. So I guess it's not technically completed yet. We can find more elements if chemists try to create them. But phosphorus does not have any similar properties to these atoms right here. So it has similar property. I had a question that asked, what do you mean by lasting? So these compounds in the very bottom, that right here, they last, they don't survive for a long time because they're really unstable and they change into other compounds. So we probably, some of them, we can have them for like a few microseconds before they totally change into another compound that's more stable. I had a question that asked if there are infinite elements, can we create infinite elements if we keep on adding protons to the nucleus? Yeah, sometimes. A warning here, for a nucleus to be stable, it needs to have enough neutrons to stabilize the protons because like charges repel each other, and too many protons in the nucleus can severely repel each other, and it would just destroy the atom. So if we can add neutrons and protons to the element, we can theoretically probably create more elements. I had another person ask if phosphorus doesn't have the same properties as sulfur. Why are the colors of the two the same? Well, this is kind of a bad chart. It doesn't color code by properties all the way. It's a similar type of molecule as these, but it doesn't have the same chemical properties. So like nitrogen gas and oxygen gas are the same, but are both gases. They don't share similar properties. I had another question that asked how many elements do you think we can make and how many elements are there? So currently chemists have found 118 elements, and there's a chance we can find more, but people aren't really looking forward to it because if we add another one, there'll be so many more elements we have to find. So now I'm going to get into metalloids and nonmetals. So metals are usually shiny solids and conduct electricity. Some common examples are like gold, silver, copper, tin, aluminum, the common things that we think of as metals. There's also elements called nonmetals that don't conduct electricity at all, and they're usually gases like nitrogen gas, oxygen gas, fluorine gas, chlorine gas. Chlorine gas is actually pretty toxic, so. And then the last group, I had a question that asked gold conducts electricity. Yes, gold does conduct electricity, but usually we don't want it to since it's a precious metal. But gold can conduct electricity, and it does pretty well. You just might destroy the solid gold into ions, though, if you're not careful. And then there's a group of elements called metalloids. So they're in between metals and nonmetals. So they're decent conductors at electricity. So that means they're really bad at conducting electricity at low temperatures like room temperatures. But if we heat them up, they're really good at electricity. So one common example is silicon, which is an important semiconductor used in electronics, so we can control the electronics. I had a question that says, if we keep adding protons to the nucleus such that more elements can be added to column 1, will the explosive behavior found in column 1 elements when combined with water keep increasing? Yes. So as you get larger and larger, it becomes more and more dangerous. So don't do it at home. It's kind of unsafe past potassium. As you go down like francium, it just creates a humongous explosion. So technically, if we discover more elements in that period, that group, it does get more and more explosive. So here's a chart that has the nonmetals, metals, and metalloids. As you can see, most of the elements on the periodic table are metals, including gold, which is right here. Oh, you can't see that. There's gold right here, silver, aluminum, which is commonly used in aluminum foil, iron, and most of the other metals that you typically see. I had a question that says, so can you just go somewhere to buy a bunch of electrons, neutrons, and protons? I guess you basically take protons, electrons, and neutrons from existing atoms. So there's not just like a free supply store that you can buy, although they do have extra neutrons at a chemical factory. How they use how they use atoms to create power. They do have supplies of neutrons, but they take them from existing atoms, so you can't just create one up. And then I had another question that says, is the explosiveness of column 1 elements combined with water increasing linearly as you go down the column, or is it increasing exponentially? It kind of depends. I don't know how you would measure explosiveness, but it does look like it increases exponentially within the first few elements, but then it might just slow down that curve later on. I had another question that says, why is there so much red in this chart compared to the other charts? So the other charts basically has properties by groups, but this one color codes them by metals, metalloids, or nonmetals. And as you can see, there's mostly metals in the periodic table. I had another question that says, what do you mean by existing atoms? So some atoms are undergo nuclear decay, and that gives you a supply of electron and neutrons. They emit neutrons when they decay to more stable forms. Sophie, I saw that you raised your hand. Do you want to type in your comment in the chat, or do you want to unmute your mic?
Okay, so why are there dashed lines at the bottom row of the main section? Like there's these dashed lines.
Do you mean the black one separating
No,
red and the?
no, at the bottom there's like in the elements.
This is an old periodic table, and at this time, these elements weren't created.
Okay.
But right now, they have been created, so.
Okay, phew.
Question. And I had another question in the chat that asked, what do the black lines mean? So the black lines is basically the separation between metals and metalloids. As I was talking about earlier, the yellow metalloids are really good semiconductors, and they're used in electronics a lot. So this black line separates the metals from metalloids. And remember, the metalloids have properties of both metals and nonmetals. I had another question that asked, what causes the explosiveness of column 1 elements combined with water? So I actually read an article about this, and scientists are still trying to figure out what causes it. Yes, you can like measure the heat released for the reaction, and you can use that to determine the explosiveness, I guess, but we still don't know what causes the explosion with the water. We just know that the group 1 elements are highly unreactive. I had another question that asks, so will the yellow on one side be more to that side than the other? No, the line is just basically a staircase, which helps us remember so it can help us remember the metalloids. So if it touches the black line, except for aluminum, it's usually a metalloid. So boron touches the black line, and that's a metalloid. Silicon does. Germanium and arsenic, antimony and tellurium, they all touch the line. So it basically just helps us remember which one is which, if it's a metalloid. So basically anyone that touches this black line is a metalloid except for aluminum. So now we're gonna do some example problems, which asks, are these elements metals, metalloids, or nonmetals? Please type in your answer in the chat when you have the answer. So our first one is SE. So try to find SE, and when you get it, please type it into the chat if it's a metal, metalloid, or nonmetal. The periodic table is color-coded, so it can help you easily see. A lot of people got the right answer. This is kind of like a scavenger hunt, basically. So if you didn't find it, it's right here, SE. So it's a non-metal. And everyone got it correct, so that's really good. It is a non-metal. How about SCS, cesium? This one's kind of harder to find. Okay, a lot of you guys have gotten it right. I'll give you a few more seconds. This one is actually one of the reactive elements that I was talking about earlier, that when you add it to water, it goes boom really big. Yep, everyone got it right. It's a metal. This one just reacts out of control. It is right here. Let me circle it. It's right here, CS. And it reacts really big with water and causes explosion. The next one, Si, silicon. Okay, I see a few correct answers. Remember, I was talking about silicon earlier, how it was a good semiconductor because it was used in electronics a lot. It is right here, and it is yellow. So it is indeed a metalloid. So good job, everyone who got it right. And we have one more, Br, bromine. Okay, a lot of you guys got it right. I'll give you a few more seconds to figure out which one it is. This one is actually a gas. Wait, no, sorry, not a gas. It's actually one of the few elements that's a liquid at room temperature, so it's pretty special. It is right here. I'll circle it in orange, Br. And it is indeed a non-metal, which all of you got it correct. So good job. So now I'll go over one more trend of the periodic table, and then we'll move on. So atomic radii, as you go down a group, the atomic radius increases due to the increased number of electrons. Like when I was talking about earlier, how hydrogen basically has 1 electron in its outer shell. And then like the group down below, lithium, it requires 3. So I'll draw the electrons in red. So lithium has 3, so there's 2 electrons in the first shell, and then in the second shell there's 1 more. So since it's in a new shell, it's in the larger. Sorry guys, I have a question in the chat and I'm trying to read through it. Okay, so I had a question about the explosion of water and using the heat released. And yes, that is what chemists use. They use the heat released to see how reactive it is. But we won't be able, but that doesn't help explain why or how it reacts, how these alkali metals react with water. We can't find the cause, but we can find out how big each explosion is in water. So I had a question that says, why are some spheres bigger than the others in the table? That's what I was getting at. So as you can see, here's hydrogen with only one electron, and hydrogen is right here, which is this tiny sphere, and lithium is this much bigger sphere. And the atomic radii increases because the electrons are in a different shell. So as you can see, as you go down, there's more and more shells. So each one of these atoms gets larger and larger and larger. It's true for this period as well. As you can see, it starts off pretty small with beryllium, and as you go down, 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 there's more and more shells, and it gets larger and larger and larger. Someone has a question. Sophie, go ahead and ask your question.
So, what is like? I'm just curious. What is like the smallest element on the periodic table? And I have two questions. That's my first one.
Okay, as you can see, the smallest one would probably be helium right here.
Okay, I can't really see that one since my screen is like fit to window.
Yeah, it's pretty small. And what was your second question?
My second question is how come like in the bottom there's like these circles that aren't filled in?
That's because that we don't actually know their sizes because they're quite unstable. So we haven't figured out their sizes yet.
Okay. So that's all.
Okay, thank you. That's a nice question. Okay, so like I said, as you go down a group, the atomic radii increases because you have more shells. But we're gonna cover one more trend on the next slide, which is when you go across a period or a row, the atomic radii decreases because there's something called a more effective nuclear charge. So as you're increasing the electrons, you're also increasing the protons when you go down. So this one, hydrogen has one proton and one electron. And this helium has two protons and two electrons. So these two protons pull in the electrons closer, so the radius would actually decrease because we know like charges attract, and protons are positive charge and electrons are negative. So when we have an additional proton, we pull in the charge, so it decreases. So that's why as you go across a row, the atomic radii decreases. So that's why helium would be the smallest, because as you go down a column, the size increases because there's more electron rows. But when you go down a row, when I mean down a row, I mean like this way, the radii decreases, and you could see it clearly in this chart. So that's basically atomic radii. And this element right here is probably going to be the largest, cesium, because it's the furthest down and it's the most left. So now I'm going to get to chemical formulas and try to finish that today. So chemical formulas is notations that use chemical symbols with numerical subscripts to see the relative proportion of atoms in a compound. So as you can see in H2O, we have two compounds bounded together. The H stands for hydrogen and the O stands for oxygen. And so this subscript tells us that there's two hydrogens for every oxygen. As you can see, the hydrogen here are blue and the oxygen is red. So this subscript tells us for every two hydrogens, there's one oxygen. So if there's no subscript behind a letter, then it's interpreted to be 1. So I'll go on. So for H2O, so for every 2 hydrogen atoms, there's 1 oxygen atom. So if we know that there's 2 hydrogen atoms, then there's going to be 1 oxygen atom. Because we can go hydrogen to oxygen is always going to be in a 2-to-1 ratio. And that's what this formula tells us. 2 hydrogens for 1 oxygen. So if there's 4 hydrogens, we want to still keep this 2-to-1 ratio. So there's a typo, sorry. It should be 2 oxygen atoms, not 3. So if there's 4 hydrogens, there's 2 oxygens. If there's 20 hydrogen atoms, there's 110 oxygen atoms. So that's basically what this formula tells us. There's a constant proportion between H and O's. So let's do the same thing for NaCl. So one thing to note is that how do we know how many different elements are in this formula? So some atomic symbols use 2 letters and some only use 1. We can tell if it's 1 element because the second letter would always be lowercase if it's a part of the first. So since A is in lowercase, this is 1 element. And this L is also in lowercase, so it's a different element. And since there's no coefficients, we know it's in a 1-to-1 ratio, which is the easiest to deal with. For every 1 sodium atom, there's 1 Cl atom, chlorine atom. So basically, if there's 1, then 1 Na, there's 1 Cl. If there's 5 Na, there's 5 Cl. If there's 20 Na, there's 20 Cl. And just saying there can be like 3 or 4 or 5 compounds stuck together, but they all have the similar proportions. Sophie's raising her hand again. Yes, so
like if you find can you go back to the previous slide?
Sure.
So if you find like a sodium atom, there's going to be a chlorine atom like that?
Yeah.
Okay.
So for every 1 sodium atom, because this compound formula tells us if we have 1 sodium, we have 1 chlorine atom. So that's what it tells us.
So the number of sodium atoms equals the number of chlorine atoms.
Yes. And that's because there's no coefficients underneath the number. But if there was like a 2 below the sodium, then for every 2 sodium atoms, there's 1 chlorine atom. So that's what the formula tells us. It tells us the proportion between the 2 different atoms. Does that make sense? Okay. So, a question that asks if you mix H2 and O together, do you get H2O? Actually, no, you don't. You have to mix hydrogen gas with oxygen gas and you get H2. I'm not talking about mixing, but in any molecule of water, for every 2 hydrogen, there's 1 oxygen. So it doesn't happen instantly. So let's do this example problem before we run out of time. So in a compound NaSH, if there are 1,005 atoms of Na and 1,005 atoms of S, how many atoms of H are there? So please put your answer in the chat when you finish. So this might be a little confusing, NaSH. But we can tell that there's 3 different elements here. The first one is Na, because the second one's lowercase, so we know that A belongs to N. And so the first element is Na. The second element is S. And we know the third one is H because it's capital, so that's a third element. So we know from the coefficient, there's no coefficients, so they're 1-to-1-to-1. So if you have 1005 of N, then you'll have 1005 of S and 1005 of H, which you guys all got correctly. So that's basically what this formula tells us. But if we have a compound like CO2, we first need to determine how many elements there are. So there's a carbon and then there's an oxygen. But this ratio of 2 tells us we have a ratio of 1 to 2. So for every 1 carbon atom, we have 2 oxygen atoms. And that's determined by this subscript down here below. And if there is no subscript, there's a 1. So we just bring them down and it's a proportion. So you guys did pretty good on that. There's one more problem. In CH2O, if there's 3 atoms of carbon and 3 atoms of oxygen, how many atoms of hydrogen are there? Okay, a lot of you got the right answer. So in CH2O, the first thing is to see how many compounds there are. Since all of them are capital letters, they're each their own compound. And it's a ratio of 1 to 2 to 1. So if we have 3 atoms of carbon and 3 atoms of oxygen, we're gonna have 6 atoms of hydrogen to balance this 1 to 2 to 1 ratio. So good job to everyone. You got all of them right. Everyone got it right. So that's how you can tell a formula, CH2O. You can tell how many atoms of each there are. So I believe there's a problem on this in your homework as well. One where you can just look at the number of atoms from a formula, chemical formula, and determine how many atoms there are. So there are 6. So today we don't have time for the chemistry Olympiad problems. I'll probably put this one in the first one of next week's lesson because we're going to tackle 2 challenging problems. As you can see right here, it's the chemistry Olympiad, and we're going to tackle those the first thing next lesson. But a lesson recap we had today, we talked about atomic mass and isotopes. And we remember isotopes are different number of neutrons, and that's how we determine the mass on a periodic table. And we learned about the periodic table trends, and we did chemical formulas, which is what we just did. So we know the relative proportion of atoms given by a formula. And the chemistry Olympiad problems we're going to do next week since we ran out of time today. And for homework, there are going to be 5 questions in a Google Forms quiz under the Classroom tab in Google Classroom. So I would highly recommend you guys doing those problems. You know, I believe there's 2 questions about isotopes, 2 questions about determining metals, metalloids, and nonmetals, and 1 question based on the chemical formulas we just had. If you have any questions or suggestions to improve this course, please contact me at this email below, and I'll post the slides later tonight. Thank you, everyone.